Hello and good morning. I hope you are in good health. First, let me introduce myself. My name is Naif. I received a bachelor's degree in computer engineering from Hoda University, Yemen, in 2007, and the master and PhD degree in communication and computer engineering from Faculty of Electrical and Electronic Engineering, University Tun Husainan, Malaysia, in 2015 and 2019, respectively. Currently, I am a lecturer and researcher in the Internet of Things at Faculty of Computer Science and Information Technology, University Tun Husainan, Malaysia. Today I am here to present our paper entitled Implementation and Analysis of an Updating Data Strategy on IAT WASP Mode Testbed for Air Quality Application. Before starting the speech, I would like to thank the committee members and organizers of this meeting. The presentation outlines are: Introduction, Motivation, Related works, Implemented algorithm, Simulations and results, Conclusion, Acknowledgement, References. Let me start with some general information on the Internet of Things and wireless sensor networks. Wireless sensor networks are increasingly gaining a big impact on our day-to-day lives. This technology has a wide range of applications in various domains, including healthcare, assisted and enhanced living scenarios, industrial and production monitoring, control networks, and many other fields. Wireless sensor network consists of spatially distributed autonomous devices that use sensors to monitor physical or environmental conditions. It integrates a gateway that provides wireless connectivity to the Internet. Various practical communications models are used in IAT implementations, and each model has its own characteristics. There are 3 models described by the IAT architecture board, which includes machine-to-machine, machine-to-cloud, machine-to-gateway-to-cloud. In Internet of Things, sensor data consist of one attribute, univariate, or multiple attributes, multivariate. Since the sensor board is only used to collect one type of data, light, temperature or humidity, this type of data is called univariate data. Similarly, in some Internet of Things applications, each sensor board is equipped with a multivariate sensor to support different application needs. As we know, battery life is a key factor in the performance of the Internet of Things applications. The size and number of transmitted packets are responsible for most of the energy consumption in IoT applications. Therefore, controlling SB operations on or off based on the status of the sensed data is one of the possible ways to decrease the number of messages sent by a sensor node, thereby saving power and extending the network lifetime. Table 1 shows a summary of the characteristics of some related works. The main contribution of this paper is to implement and analyzes an updating data strategy on IAT sensor board for air quality application in different locations.
This paper provided an implementation and analysis of an update data strategy on IAT WASP mode gases testbed with 2.4 GHz XB. The studied algorithm enables efficient data collection and dissemination for IoT, denoted as EDCD1 and EDCD2 for sensor board with a single sensor and multiple sensors, respectively. EDCD1 and EDCD2 have been explained in detail in reference 12. Figure 1 shown the flowchart of EDCD algorithm. EDCD algorithm is intended to reduce the number of the transmitted packets via IoT edge, supporting single and multiple sensors based on relative differences between the current and last sensor measurements transmitted, where RF is the relative difference value between the new real-time sensed data at the time t and the last sensed data transmitted to the gateway at t1, and beta is the threshold and its value set to 0 in this study. It should to be noted that our previous work in reference 12 provided merely a simulation results. Hence, this paper presented a prototyping system with implementation of the EDCD algorithm for real-time air quality measurement application. Implementation and evaluation. First, let me describe system prototyping. The system items used in this study are WASP-Mode gases board, XBEE Pro 802.15.4, humidity sensor, temperature sensor, carbon dioxide CO2 sensor, oxygen O2 sensor, and battery. XCTU tools used for setting the sensor node XB and gateway XB. XCTU is free software provided by Digi International. In addition, XCTU serial console is used to capture the sensed data from IoT gases testbed sensor node. In this study, the sensor node is used to sense the air quality gases for different locations as follows. The first location at RACAD Lab Indoor. Second location at FKEEQ Block Outdoor. And third location at My Home Indoor. Figure 4 shows the sensor node integrated items. WASP-Mode Pro ID based C++ was used to write the algorithm code in the sensor board level. Results and discussion. In this study, the results are divided into two scenarios. The first scenario shows the results of applying EDCD1 for a single sensor, where we only used the IoT WASP-Mode gases board to monitor the temperature or humidity sensor at two locations, home and RACD lab. Figure 2 showed the energy consumption for IoT sensor board in active mode in different scenarios. It could be noted that the sensor board with multivariate sensors will be lost more energy compared to the sensor board with a single sensor. Figure 6 showed the results of applying EDCD1 versus without algorithm for temperature and humidity sensors in terms of the size of received data in bytes for two locations, home and RACAD lab. It is clear that controlling the operation of the transmitter XB on or off has a positive effect in terms of reducing the amount of transmitted data in bytes compared without using EDCD1 algorithm, which will help in saving the IoT sensor node energy. The amount of transmitted data when the IoT sensor node is located in home has been reduced from 4,140 bytes to 1518. And 1,120 bytes for temperature and humidity sensors, respectively. Despite using the same sensors to monitor the temperature and humidity inside RACAD lab, the amount of reduced data is larger than my home. This is due to a slow change in the value of the sensors inside the RACAD lab. Because the air condition remained turned on during the experiment. Therefore, EDCD1 algorithm shows better performance than the home without air condition. 7 and Figure 8 showed the results of applying EDCD2 on IoT WASP-Mode gases board for monitoring the air quality in different locations such as RACAD Lab Indoor, Perwara Home Indoor and FKEE Outdoor. It should be noted that in this scenario, the sensor board payload data included multiple sensors at the same time. Therefore, the size of the payload data is larger than the payload data in the first scenario, which contains only one sensor. So for that we applied EDCD1. In this part, the total number of received packets is 60 and the size of received data was about 6,000 bytes without the use of EDCD2 for all sensing areas or locations. Conversely, applying EDCD2 reduced the number of transmitted packets by 27, 25, and 19 packets for Perwira My Home, FKEE Outdoor and RACAD Lab, respectively. From the results we inferred that change the sensing area and environment location affected the performance of EDCD algorithm. Conclusion. Battery life is a key factor in the performance of the Internet of Things IoT applications. The size and number of transmitted packets are responsible for most of the energy consumption in IoT applications. Therefore, controlling XB operations on or off based on the status of the sensed data is one of the possible ways to decrease the number of messages sent by a sensor node, thereby saving power and extending the network lifetime. Hence, this paper provides an implementation and analysis of an update data strategy on LOT WASP-mode gases testbed with 2.4 GHz XB. The studied algorithm enables efficient data collection and dissemination (EDCD) for IoT sensor board denoted as EDCD1 and EDCD2 for sensor board with a single sensor and multiple sensors, respectively. The EDCD has been applied on LOT WASP-mode gases testbed for monitoring the air quality in various locations. The experimental results indicate that the EDCD algorithm performance is affected by the type of sensor as well as the sensing area location. Overall, EDCD algorithm showed acceptable performance for IoT WASP-mode gases testbed with 2.4 GHz XB. In addition, there is no delay in receiving data from the sensor node after applying the algorithm compared to directly transmitting data. Acknowledgement. The authors would like to express their thanks to University Tun Hussein An Malaysia UTHM for support. This research is supported by the University Tun Hussein An Malaysia under Grant U897 TIER1. References. Thank you.